In this example, two parts. We want to find the equation of the line of intersection of the two planes, and then in the second part, we want to use that line of intersection to find an equation of the plane, another plane, containing that line and the point 314. So in part A, starting with finding the equation of the line of intersection. The equation of a line, r of t, it's going to be in terms of t. So we want to parameterize these two equations so that we can solve for our x, y, and z components in terms of t. So I'm going to rewrite, copy down these equations again. And I'm going to call my first equation equation 1, and we'll call the second one equation 2. We need to eliminate one of these variables, because if we can get our equation in terms of just two variables, then we can let t equal one of the variables and then solve for the other variable in terms of t. Looking at the y component of the second equation, if we multiplied it by 2, and then added it to the first equation, then the y component would cancel out. So let's multiply the second equation by 2. And that gives us 4x minus 2y plus 2z equal to negative 6. And I'll call this equation 3. So now we want to add equation 1 and 2. Rather, equation 1 and 3, so that we can have our y's cancel out. And so we have x plus 4x gives us a 5x. We have a positive 2y minus 2y is 0. And then for our z components, we have 3z plus 2z, so plus 5z. And then that is equal to 1 plus negative 6, which is negative 5. And let's divide through both sides of this equation by 5. So we have x plus c is negative 1. Okay, so at this point you can let one of the variables equal t. It doesn't matter which one. I'm going to let x equal t. And letting x equal to t and solving for z, we get that z is equal to negative 1 minus t. So now in terms of the equation of our line, the equation of the line of intersection, we know our x component is t. We know that our z component is negative 1 minus t, and we just need to solve for our y component. So to do that, let's sub that back into the second equation. And subbing into the second equation, we have 2t minus y plus our z is negative 1 minus t, and that is equal to negative 3. So solving for y and then getting everything else on the other side, we have 2t minus 1 minus t. Let's add 3 to both sides and then add y to both sides. And simplifying, we get that y is equal to 2t minus t is t, and then minus 1 plus 3 is plus 2. And so that is our y component, t plus 2. And now we have our line of intersection of the two planes. And so in part B, we want to find an equation of the plane that is containing this line and the point 314. Okay. I think that it's always helpful there to start with a sketch of just what we're dealing with. So I started by sketching r of t, our line, and our point P. Now, to find the equation of a plane, we need a normal vector and a point. In order to find the normal vector, we need two vectors that lie in the plane. And in order to find vectors that lie in the plane, we need 3 points. So our goal here is going to find 2 points that lie on the line r of t, and then use that and the point P to find two vectors. So let's start by finding at t equal to 0. Say r of 0 is 0 to negative 1. And then let's call that point that it represents 0. And plotting that on our sketch, we now have our 2 points. We can see we can easily form the vector 0p. And so 0p would be p, 314 minus the 0 to negative 1, and that gives us one of our two vectors. Then to find the other vector, we know that the direction vector of r of t lies on the line with its tail at r of 0. So if you actually found r of 1 minus r of 0, that would be the direction vector. So sketching our direction vector now, the direction vector of this line is 1, 1, negative 1. I'll probably pull my z component out of there. But it's going to keep popping up on the following slides. So now sketching that, we have our direction vector is 1, 1, negative 1. Now we have our two vectors, and we can use the two vectors to find the normal vector. And we know algebraically that the normal vector is the cross product of dr and op. And since I drew my vector pointing up and I want to follow the right-hand rule, I will do the dr first, so dr cross op. And so for finding that cross product, we'll go back here. So for finding that cross product, that is equal to I like using the determinant method, but you are certainly welcome to use the basket weave cross-hatching method if you prefer. So using the determinant method, in the top row we have I, j, k. In the second row we have our direction vector, 1, 1, negative 1. And in the bottom row we have OP, so 3, negative 1, 5. Okay, and this is equal to, so for our I component, we would have 1 times 5 minus negative 1 times negative 1 minus our j component. So for j, we would have 1 times 5 minus 3 times negative 1 plus, and for our k component, we have 1 times negative 1 minus 3 times 1 and move that over slightly so I have room for the k. Okay, there we go. So simplifying that, we have 5 minus a minus a minus is a negative, so 5 minus 1 is 4i. Then minus 8j. And in our k component, we have negative 1 minus 3, so a negative 4k. So now we have the equation of our normal vector and we have our point 314. We can use that to find the equation of the plane. Containing our line of intersection and the point, that is going to be 4 times x minus 3 minus 8 y minus 1 minus 4 z minus 4 equal to 0. And you don't need to simplify. This is the preferred form that we'd like you to leave it in.